Whether we're interested in developing compaction curves themselves, or we're interested in the engineering properties and how those change as a function of the compaction conditions, we need to be sure that we prepare the soil to the right water content before we run the experiments. So in the case of cohesive soil, this is Young Bay mud. It's been used before. It's been oven dried, ground to break up the high dry strength clods again, and then left in the lab under sort of typical ambient conditions. And we have to be careful. This is not dry material. It's currently around 4% water content. And so if we want to hit some other target water content, we need to account for what's already in there. And then just add the amount that we need to bring it up to the water content we want. So right now, for this, we're going to be mixing up 1.65 kilograms of the bay mud at the ambient conditions, and we're going to be adding about 300 grams of water to do that. Because it's a plastic soil, if we just poured in 300 grams and stirred it with a big spoon, we'd probably end up with some very sticky parts and some dry parts. And so we're going to use this Lancaster mixer, paddle mixer, shear mixer, to gradually add that water and try and avoid that non-uniformity problem. So we're going to start with the blades down on the bottom first, then we're going to add our dry soil. When I say dry, you should catch me there, right? Not completely dry, 4% water content, despite all this dust. And then this is a reservoir on the top with a nozzle for spraying in the water. We're going to have an air pressurized system on the top for that. So we've weighed out 300 grams of water. We're going to add that to the reservoir. Then we're going to start turning the mixer before we actually start adding the water. So it's going to get a little bit loud, so I'll get everything else ready first. So we have a small air pressure on here, maybe an atmosphere. And we're going to turn this on. The paddle mixer will keep churning the soil around, mixing the soil around, and the water will get added slowly. So all the water has now been forced out through the nozzle into the soil, and we have a relatively uniform mixture here, so we can stop the rotation. Take the air pressure off. Turning the mixer for more time often doesn't help very much, even if it isn't completely uniform. And you'll get some larger and larger clods, depending on the moisture content you're working at and the plasticity of the soil you're working at. They'll just get very, very large and grow. So we're going to stop there. We'll take the soil out. We're going to seal it in a Ziploc bag so that the moisture can't change. And then, very importantly, for plastic soil, we need to let it cure. So overnight, 16 hours, before we actually go ahead and either run a compaction test on the soil or use it in some other way to measure properties of the compacted material, because it takes time, again, for the water and the moisture to come into equilibrium with clay that is relatively dry until right before that. So that gives time for the double layers to get into equilibrium and those things. To measure the triaxial strength of a compacted clay soil, we're going to use the same equipment, the triaxial equipment that we used for the UU test and the CU triaxial test. But instead of taking a block or a larger sample of the bay mud in this case and trimming it down to the specimen geometry that we want very carefully, we're instead going to create or reconstitute the same geometry specimen but in a cylindrical mold using collars and, in this case, a Harvard miniature compaction hammer, which is this system here. We'll talk about more in a few minutes. And of course, we're going to want to work with bulk sample of the soil that's mixed up to the water content that we want and been allowed to cure overnight. So we have all the materials here and we can get started. The Harvard compactor works essentially as a sort of an air spring. You can see that the hammer consists of a rod within a chamber up here. There's an air pressure that acts on the top of that chamber, and I can control that air pressure through an accumulator and a regulator that I can adjust, therefore, the amount of force it's going to take to first initiate motion as I'm pushing down. So if I'm pushing with a light force, I'm not going to get any movement in this rod until I push down with enough force that I overcome the air pressure acting on the cylinder, at which point it'll suddenly start to move. And as soon as this suddenly starts to move, I want to stop pushing. So in a sense, it's an adjustable way to set the force at which this tamper is used, but it's not a mechanical system really. It still depends on the operator to provide that force. It's a pretty loud system as a pneumatic system, so I'm not going to turn the pressures on until we're about ready to go, but that's how it works. In terms of a procedure for compaction, there's no standard like there is for the modified AASHTO or the standard Proctor in terms of the number of layers or the number of tamps or the pressure that we set it at. Really, we're just looking for a repeatable, systematic number of tamps per layer where there's a certain approximate mass in each layer that's the same all the way up through the specimen so that we get a uniform specimen. And then it's sort of a trial and error process. We build a specimen, we see what our procedure has created for this soil at this moisture content. You know, what density is that? Is that what we want? If we want something denser, then we need to turn up the pressure on the hammer or do more tamps or thinner layers or whatever adjustments we want to make. Then once we find what we want, we can repeat that and get essentially the same answer from one specimen to the next. So we're going to start by putting in 2 tablespoons of soil. So like the cooking show here. And we'll turn on the pressures. It'll get loud then, so I'll do my talking now. I think we'll apply 20 tamps. We're going to set the pressure here up to 20 as well. And we'll see, my experience, I think that'll be relatively good density for the moisture content we have here. In between layers, it's probably a good idea to seal up the bag so we don't lose moisture content and dry out the material. So here we go, let's get some pressure on. We'll dial this up to 20. And so now, this is a rigid system. I can't easily push this at all, but if I lean on it a little bit, oh, that's actually a little too easy to move. I'm going to turn it up to 30. Okay, so now I have to apply significant force get that piston to first move. So here we go. Let's do our 20 tamps. Actually, yeah, here we go. 1, 2. I have my 20 tamps. There was a little bit of movement of the loose soil when I first started, but it looks pretty good now. And so we'll continue that process to fill the mold all the way up to the top, into the collar. Then we can remove the collar afterwards and extrude the sample from the mold. So we've compacted the soil now up in a number of layers, 8 layers, up above the top of the mold itself and into the collar, so we can turn off the air pressure. A little more peaceful. And one of the things I wanted to point out, unlike standard Proctor or modified Ashto compaction hammer, the area of the hammer is quite small, and so it's well under half the diameter of the specimen itself. In a compaction test with a modified Ashto hammer, say, the hammer's half the diameter of the mold, and so you don't have to do any extra tamping in the middle of the specimen. If you just go around the edge, you cover the whole specimen adequately. But the point of the Harvard compactor is it's supposed to represent kneading compaction. So we want to be pushing the soil down and shearing it as we compact it. So we do need to spend some of those tamps tamping the soil in the middle of the specimen as well, which is one of the reasons you need sometimes more tamps with this to get a good uniform material. So we can take our mold part, and we have a nice smooth surface on the bottom there against the base cap here, base plate. And if we twist this gently, okay, we can just remove the collar. You can see how shiny this material is. We've compacted it nice and tight out against the cylindrical mold. Now though, we need to be able to extrude it out, and that might be rather difficult. I think I'm going to bring over the extruder so you'll get a chance to see how that works as well. So this extrusion device is what we use for most undisturbed samples of more conventional size. It's basically designed with a spring ring clamp here that'll clamp onto a Shelby tube. And if we have a Shelby tube, we can put the appropriate sized disc in there that'll just clear the Shelby tube, and clamp the tube on the outside with a C-clamp, say, or a bolt. And then it's basically just a hydraulic jack. We're just pushing that central rod vertically up, smoothly up, since it's hydraulics, and pushing the soil smoothly out the top of the sample tube, keeping the direction of movement the same. If we want to extrude a smaller specimen, then we need to put in some extra pieces that can accommodate and hold the smaller mold. So we have this insert that we can put in, and I'm going to lower this out of the way. Flush at the bottom there, and then place the soil specimen in. You can see there's a notch here. This bar is just going to reach across and latch into that notch. You can see there's some cracks from when we had a lot of trouble getting samples out of this sometimes. See how it works today. And before we extrude it even out of here, now is a good opportunity to trim off that excess soil at the top, because while it's still in the mold, we have a nice flat reference around the edge against which we can trim it and know that the top surface of the specimen will be parallel with the bottom surface. If you extrude it first, it becomes very hard to trim the ends of this. And that's mostly because you can see this is trimming, it's like chocolate shavings. This is not the same texture that we saw in the naturally occurring bay mud retrieved from depths in the boring, right? Which was very soft. We could carve it with a wire saw. You would have a lot of trouble trimming this material that way. It's much denser, it's much drier now, right? So let's see if we can get this out without a lot of grief. There we go. Not bad. Okay. And so this is the way we extrude most of our undisturbed samples in Shelby tubes or other similar tube samples, always vertically. A lot of labs you'll see people extruding samples horizontally, but then you've got some kind of a, gravity is working to bend your sample, whereas here we're just pushing the soil straight up, hopefully without a lot of disturbance. So there's our specimen. We can roll this out of the way. And I was a little bit gentle holding it there, but this is not like the bay mud specimens that we trimmed from the natural deposit, right? It's much stronger. It's got capillary tension, right, that we built in by shearing and compacting the soil with a non-saturated water content, right? So we have all those menisci in there holding the structure together. So we can actually just grab a calipers, we can measure the height, we can measure the diameter, we could wrap a pie tape around it if we had a small one to get a pretty accurate volume. We don't have to worry about damaging it the way we would an in situ material or an intact material from the below the ground surface. So, and of course the other thing we want to do is take it over to the scale and get a moist mass. So that's going to give us the moist mass and the volume based on its dimensions. That gives us our moist density. At the end of the test, we'll dry the whole thing in an oven, all the solids, we'll get a mass of the dry solids, and we'll be able to calculate both the water content from that as well as obviously what the actual dry density of the material in the test was. So we're going to set up the triaxial cell similar to the way we set it up for the UU test. We have one membrane on, we have an O-ring sealing that membrane to the bottom cap. We're going to put in a porous stone. In this case, mostly just to give the sample sort of a good grip there, have a frictional surface. The sample can fit in there. And we want to get it relatively centered. This sample is actually a little taller than the UU sample. The mold is a little taller, so I don't think I'm going to put a top porous stone on. I want to make sure I don't crunch anything. And then, what about filter paper? Well, that depends. Actually, it doesn't depend too much. If this was going to be a soaked specimen that I was going to need to get air out of and water into, I would probably want to put a different top cap on the top, one that had a drain line. I'd want to be able to use this top drain line on there so that I could actually access both ends of the specimen. And in fact, what we often do is we run the permeability tests on compacted soil in just that way. We build the specimen just like this, we use a top cap with a drain line. We attach that drain line here, and then we have access to the top cap through this valve and to the bottom cap through this valve. And by doing that, not only can we access both ends of the sample, but we can apply different back pressures to each end of the sample and watch as water flows under the gradient there. So hopefully we'll do that a little later in the semester. But for this sample, we're going to run an as compacted test. So we don't need to get water in, we don't need to get air out. So we're just going to put on a top cap with no drain line, and we can just roll this membrane up. It's not a panic for this soil. The membrane can't damage this specimen the way that it can crush the undisturbed bay mud at the high water contents. So I don't have to go through an elaborate process of putting the top of the cell on and all of that. And in fact, the membrane here is keeping the chamber pressure independent, obviously, from the pore pressure. So we will probably actually vent the pressure just to the air outside, so that if we apply chamber pressure, we know we have that gradient and there's no buildup of pressure inside the pore space. So we can assemble our chamber, put on the top. Where's the 38? There it is. Make sure I'm not in contact. No, that looks good. And because we're going to be running this in the as compacted state, we don't need to worry about filling the chamber with water either, really. If we wanted to go to very large pressures in the chamber for some reason, we'd probably want to put water in the chamber just as a safety measure, but we're not going to be doing that today. So, where did I put the loading rods? Here they are. So you can see this is a small, thin diameter loading rod. It fits right in the top of the cap there. And we're pretty much ready to go take this over to the track-seal device and prepare for the test. So to run the track-seal strength testing on the compacted clay specimen, we place the cell here. We're using a more sophisticated track-seal system. As we get later into the semester, we're going to use this also for the cyclic testing, the dynamic properties later on. So we have a frame here, load cell, loaded by a pneumatic piston that has two separate air supplies, one to the bottom and one to the top. And those are connected to this box, which has the EP valves, the electropneumatic valves, by which the computer can control the pressure that's sent to the top of the piston. So now, in addition to having the computer record data in terms of the load cell, the LVDT that we're going to mount, and our cell pressure, effective pressure transducers, and the volume change transducer. So there's 5 channels the computer's going to record, but it's also going to watch those channels, and the system is going to control the chamber pressure based on what we ask for, and it's also going to control the pressure on the top of the piston. So for a compression test like we're going to run today, we're going to give it a loading schedule, and the computer is going to apply the pressure at the rate that we ask for. So it's computer controlled as well as the computer data acquisition. Those 5 channels are down here on the signal conditioner box, so we can adjust the gains, we can adjust the zeros of the individual transducers down there. So that's sort of the intermediary between the computer that wants to read things and send things in volts, and the individual transducers, which operate on different principles and require, they're obviously measuring things in units of kilograms or millimeters or kilopascals. So we'll get this connected to the system, look a little bit at the software, and then we'll run the test. As part of the input to the software, I need to enter the specimen diameter, the specimen height, because the software is going to be taking the readings of kilograms and millimeters of displacement and automatically correcting, or not correcting, but converting those, interpreting those in terms of stresses, in terms of deviator stress, shear stress, axial strain, etc. So it's important that these be right, but on the bright side, you don't have to go through that post-processing in the same detail because it's calculating it for you. It even goes so far as to ask you what is the loading rod diameter that's sticking through the chamber. So based on whatever the chamber pressure is, the computer has the information it needs to calculate what the uplift is and automatically correct the measured load for the uplift before it calculates the deviator stress. So it does takes a lot of the post-processing out of the system. I'd like to point out too that the system we're using is labeled there on the main mechanical box as a CKC, cyclic loader. This was developed by Clarence K. Chan, that's the CKC. He was my predecessor here at Berkeley. He worked closely with Professors Harry Seed and Jim Mitchell in developing a lot of the modern testing equipment. So for example, this was, I don't know, this is perhaps third or fourth generation from his initial prototypes in learning how to develop cyclic loading for soils, for example. So he's still living over in San Francisco. He's been retired a long time, but these systems are found around the world and are really helpful for performing research because you can have a certain degree of flexibility. Even though they're relatively simple to use, they're not black box systems. So we really rely on them here in the Berkeley labs. The software for the system is menu driven. So this is the kind of home test menu. You can see it has different modules for back pressure saturation and B-value checks, which are all very automated and straightforward. Consolidation, not one-dimensional consolidation, but consolidation of your triaxial specimen. That can be unloading or positive loading. Conventional compression and extension. If you want to run extension tests, it's set up to do that. Static cyclic loading test, kind of a funny name, but it means it's a slower controlled cyclic loading, which is closed loop. It's monitoring the stresses continuously, so we can't go as high a frequency. The dynamic test, which is for higher earthquake sort of frequencies, an open loop test, and even fancier things, creep and relaxation, arbitrary stress path tests where you just move from point to point in stress space, and a K-naught consolidation as well if you were interested in anisotropically consolidating. So we're going to just be simply running conventional compression, and we'll set that up and get it ready to go. We've selected a chamber pressure or effective consolidation stress of 50 kilopascals, half an atmosphere, which is modest for a fill, but it's, you know, not right at the surface. And we're going to load it at 50 kilopascals per minute of axial stress. That sounds like a lot after looking at the soft Young Bay mud underground, but you'll see that that's this is not that short a test. So we'll go ahead and start it here now, and then I'll move the camera over and we'll watch the sample respond. I do want to show you the graphs that we're going to see in real time. So on the upper right corner is the stress path plot. Actually, yeah, deviator stress versus mean effective stress. The deviator stress versus time is in the bottom right. In the lower left is volumetric strain with axial strain. Not much going to happen there because it's not connected. We're not going to see any volume change. But the upper left is essentially the stress strain curve, the deviator stress versus axial strain. So you can see we got a little bit of strain early on when we got better seating, and now it's climbing up to 30, 35, 40 because we asked for 50 kPa per minute. So I'm going to shift the camera over to the sample and we'll watch the deformations from there. So the deviator stress is currently about 65 kilopascals. The strain is still perhaps 0.1%, so it's very steep stress strain curve. The material is very stiff. This is consistent with that really high effective stress. You know, we have 50 kilopascals of chamber pressure on, but the negative pore water pressure inside the as compacted soil fabric is probably multiple atmospheres of pore water tension. So it's very stiff material. We're still seeing very little strain. Stress strain curve is bending over now though. The stiffness is definitely reducing somewhat. More strains for a given stress increment. (440 kilopascals) deviator stress. (2% strain. Definitely bending over now though. Up close to 3% strain, 480 kPa. (500 kPa). Almost horizontal though. Strains are going up very fast. Very close to failure. There we go. So peak a little over 500 deviator stress. And here's the screen. You can see the stress strain curve in the upper left. Don't take the post-peak part of that with too seriously, because that all occurred in the space of about a second, right? So that's interpolating just a couple data points. But up to the peak, it should be very good.